Antiderivatives. A function capital F is called an antiderivative of lowercase f on an interval I if the derivative of capital F is equal to lowercase f for all numbers in the interval. So let me give you an example of this definition. We know that if capital f of x is equal to x squared, the derivative of this would be 2x. So what we could say here is that if f of x is equal to 2x, this means capital F of x equals x squared is an antiderivative of lowercase f. What we need to focus on is why do they say it is an antiderivative instead of the antiderivative? And the reason for this is very simple. Imagine if capital F of x were equal to x squared plus 3. The derivative of this function would still only be 2x. And therefore, if lowercase f of x is 2x, then uppercase f of x equals x squared plus 3 is also an antiderivative of f of x. And in fact, if you're given a particular function, there would be infinitely many antiderivatives. For example, if capital F of x is equal to x squared, or capital F of x is equal to x squared plus 3, or capital F of x is equal to x squared minus 5, or in fact, if capital F of x is equal to x squared plus any constant c, then the derivative is going to be 2x. So when we talk about an antiderivative of a function, the first thing to realize is that there are many antiderivatives of a function. So now we have a theorem that says if capital F is an antiderivative of lowercase f, then the most general antiderivative of lowercase f is capital F plus c, where c is some arbitrary constant. And this is pretty much what I alluded to just a moment ago. So let's assume that f of x is equal to 2x. We know that one of your antiderivatives could be x squared. And this is because if we take the derivative of x squared, we get 2x. So since we know that capital F equals x squared is one of your antiderivatives of 2x, then the most general antiderivative would be x squared plus c. And so what this means is that when you are finding an antiderivative, you always need to remember to add this arbitrary constant to whatever you find for your antiderivative. Let's take a look at some examples. So here we are asked to find the most general antiderivative of each of the following functions. So let's just start with the first one here. We have f of x is equal to sine of x. And so we have to ask ourselves the question, what function has a derivative of sine of x? So let's think about this for just a minute. If y is equal to cosine of x, we know that dy dx is negative sine of x. So that's not quite it. But if our original function were negative cosine of x, then the derivative of negative cosine would be negative negative sine of x. And this would indeed be sine of x. So the answer to the question here, what function has a derivative of sine of x, is right here, negative cosine of x. So what is the most general antiderivative then of sine of x? So let me go ahead and use my notation. The most general antiderivative of lowercase f of x equals sine of x is going to be uppercase f of x is equal to negative cosine of x, but then we have to remember to add an arbitrary constant. And this is because if I take the derivative of this function, the derivative of c, of course, is 0. So it does not affect the outcome of the derivative. Let's take a look at part B. What is the most general antiderivative of 1 over x? Well, you might remember that if y is equal to the natural log of x, then dy dx is 1 over x. So at first glance, you'd like to say that the most general antiderivative is in fact natural log of x. But that's not entirely true. In fact, if y is equal to the natural log of the absolute value of x, you can define this to be one of two things. You can say the natural log of the absolute value of x is the natural log of x if x is already positive, and it is natural log of negative x if x happens to be a negative. And this is because if you plug in a negative number, what the absolute value actually does is it takes the opposite of that negative number. So if y is equal to the natural log of the absolute value of x, the derivative is going to be the derivative of each one of these. So the derivative of natural log of x, of course, we know is 1 over x. But then what's the derivative of natural log of negative x? Well, it's actually 1 over negative x times the derivative of negative x, which is negative 1, and that is also 1 over x. So in fact, if your function is 1 over x, your antiderivative isn't just natural log of x, it is the natural log of the absolute value of x. So our most general antiderivative is going to be capital F of x is equal to the natural log of the absolute value of x plus our arbitrary constant. So now, what would be the most general antiderivative of the function x to the n? And notice that we say n cannot be negative 1. Now, real quick, the reason n can't be negative 1 is because if you have x to the negative 1, this is in fact 1 over x, which is what we did here. So x to the n is going to assume that n is not negative 1. So what would be the most general antiderivative of x to the n? Well, let me just posit this. Suppose I let y equal x to the n plus 1 power divided by n plus 1. If this is the case, then dy dx, the derivative, would be n plus 1 x to the n plus 1 minus 1, and then over the constant n plus 1. Now just take a look at this. The n plus 1 is going to cancel out here, and n plus 1 minus 1 is just n, so this becomes x to the n. So we can see just by simple inspection that if y is the function x to the n plus 1 over n plus 1, the derivative is clearly x to the n power. So if we start with our function x to the n, the antiderivative must be this function here. So I'm going to say capital F of x must be x to the n plus 1 over n plus 1 plus our arbitrary constant. And we'll keep in mind here that n cannot be equal to negative 1. And this is actually really clear if you look at the function here. If n is -1, we have a problem here with dividing by 0. So once again, that's just another reason why we are avoiding n equals -1. So now we have a table of anti-differentiation formulas. So these are formulas that you will be expected to know. So first, if you have a constant multiplied by a function, the antiderivative is simply that constant multiplied by the antiderivative of that function. Second, if you have the sum of two functions, its antiderivative is the sum of the antiderivative of each one of these functions. Now we get into some of the other things. So the antiderivative of x to the n, as we just discussed, is x to the n plus 1 over n plus 1. The antiderivative of 1 over x is the natural log of the absolute value of x. The easiest one is the antiderivative of e to the x is e to the x, because we know the derivative of e to the x is e to the x. And here's one that you may not have remembered here, but the antiderivative of b to the x is b to the x divided by the natural log of b. Now, why is that? Well, it's because when you take the derivative of b to the x, you get b to the x times the natural log of b. Don't worry too much about this one right now. The antiderivative of cosine is sine, clearly, because the derivative of sine is cosine. As we discussed a few moments ago, antiderivative of sine is negative cosine. And of course, the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared. Likewise, the antiderivative of secant times tangent is secant, for the same reason. And then a couple of special cases here. The antiderivative of 1 over the square root of 1 minus x squared is the inverse sine of x, and the antiderivative of 1 over 1 plus x squared is inverse tangent of x. And we won't concern ourselves with these antiderivatives at the moment. These are hyperbolic trigonometric functions. They're important later, but not as much right now. So in our next example, we have g prime of x is 4 times the sine of x plus 2x to the 5th power minus the square root of x over x. And we want to find all functions g such that this is true. So in other words, you are being asked to find the most general antiderivative of g prime. So the first step in finding the most general antiderivative of g prime here is to algebraically manipulate this expression. So I'm going to rewrite this as 4 sine of x plus, and then we'll have 2x to the 5th power divided by x minus the square root of x divided by x. So I'm just basically separating this into two fractions. Let's also remember that x is the same as x to the 1, and the square root of x can be rewritten as x to the 1/2 power. And this now allows us to subtract these exponents. So 2x to the 5th divided by x to the 1 is 2x to the 4th, minus, and then here we have x to the 1/2 take away 1, which is the negative 1/2 power. Now keep in mind, this is still g prime of x. But now this allows us to use the formula for finding the antiderivative of x to a power. But first, let's go ahead and start here. So now I'm going to write capital G, or actually I'll just write lowercase g. That's the appropriate notation here because this is g prime. So the antiderivative would just be called g. So the antiderivative here, we have 4 times the antiderivative of sine, which we know is negative cosine, plus we have 2 times the antiderivative of x to the 4th is x to the 4 plus 1 over 4 plus 1, so we're using that power rule there, minus, and then the antiderivative of x to the negative 1/2 is x to the negative 1/2 plus 1 divided by negative 1/2 plus 1. And then don't forget to add your arbitrary constant. Now, we need to simplify this. This is not okay as an answer here. So 4 times negative cosine can be rewritten as negative 4 cosine of x. Plus, then we have 2x to the 5th power divided by 5. Minus, next we have x to the 1/2 power divided by 1/2 plus c. And the only thing left to do here is to not leave our answer as a complex fraction. So I'm going to rewrite my final answer here as negative 4 cosine of x plus 2x to the 5th power over 5 minus, let's remember when you divide by 1/2, that's the same as multiplying by 2. And so this is our final answer. And the one other thing that you could do here is you could change this to be the square root of x. And this is our most general antiderivative. In our next example, we want to find f if f prime is equal to the function you see here. So let's go ahead and write down f prime of x is equal to e to the x plus 20 times 1 plus x squared quantity to the negative 1. And then we're also given this extra piece of information, f of 0 equals negative 2. And we'll talk about this at the end of the problem. But let's just focus on getting the antiderivative. Now, what is really important here is to recognize that you cannot use the power rule here. Okay, so let's remember the power rule says that if you have x to the n, the antiderivative is x to the n plus 1 divided by n plus 1. But this only works if you have a base of x. It does not work with another base. So we cannot use the power rule here. So instead, I'm just going to algebraically rewrite this once again as e to the x plus 20 times, and then 1 plus x squared to the negative 1 is 1 over 1 plus x squared. And now we can find the antiderivative. Of course, the antiderivative of e to the x is just e to the x. Plus, then we have a constant 20 multiplied by, what is the antiderivative of 1 over 1 plus x squared? Well, we should recognize that 1 over 1 plus x squared is the derivative of the inverse tangent. Therefore, the antiderivative of it would be inverse tangent. And then plus c. Now, usually this would be our final answer. But what they've given you here is something called an initial condition. And what that means is that we know that f of x, whatever it is a function that when you plug in x equals 0, you get y equals negative 2. What this basically allows us to do is it allows us to solve for a specific value of c. So I'm going to let f of x equal negative 2, while I let x equal 0. So now we need to know that e to the 0 is 1. Then we have plus 20 times the inverse tangent of 0 is 0. And this says negative 2 is equal to 1 plus c, because 20 times 0 is 0. And this means that c must be equal to negative 3. So we can improve upon our answer by giving a specific constant. So c is negative 3, which leads us to this function. So this is no longer a general antiderivative. This is a very specific antiderivative. In fact, it is the antiderivative of the function that also passes through the point 0, negative 2. Our next example is very similar to the previous one. Here we have the second derivative of some function f is equal to 12x squared plus 6x minus 4. And then we are given two pieces of information, f of 0 equals 4 and f of 1 is equal to 1. So if I want to solve for f of x, notice that you have to take an antiderivative twice because we start with the second derivative of some function. So to get the first derivative, we have to take the antiderivative of the second derivative. So the antiderivative of 12x squared is going to be 12 times x to the 2 plus 1 divided by 2 plus 1, so that is the power rule, plus 6 times x to the 1 plus 1 divided by 1 plus 1. And then let's remember that the antiderivative of negative 4 is simply negative 4x because we know the derivative of negative 4x is negative 4. And then we're going to have plus a constant of integration. And I'm going to call this C1, and you'll see why in just a moment. But now I can simplify f prime of x is going to be 12x to the third power divided by 3. So 12 divided by 3 is 4. So I can write that as 4x to the third power. Plus, then we have 6x to the second power divided by 2. So 6 divided by 2 is 3. And then x to the second power minus 4x plus C1. Now, most of the time, if we're given information here, we would then find this constant. But here's the thing. You cannot plug this information into this function. Can you see why? Well, yeah, it's because this is f prime, not f. And both of these involve f, not f prime. So unfortunately, we will temporarily not know what C1 is. So let's go ahead and find f of x now by taking the antiderivative of these. So the antiderivative of 4x cubed is going to be 4 times x to the 3 plus 1 divided by 3 plus 1, plus 3 times the antiderivative of x squared is x to the 2 plus 1 divided by 2 plus 1, minus 4x to the 1 plus 1 divided by 1 plus 1. And then the antiderivative of C1 is simply C1 times x. Because remember, C1 is a number. We just don't know what it is right now. And then we get a new constant of integration, or constant of antidifferentiation, at the end of this process. And we'll call that C2. So the reason I called this one C1 is because I want to be able to tell these apart. So now let's write down what f of x is. So we have 4x to the fourth divided by 4, which is just x to the fourth, plus 3x to the third divided by 3, which is just x to the third, minus 4x to the 2 divided by 2, which is going to be minus 2x squared, and then plus C1 times x plus C2. Now, if what they asked for was the most general antiderivative, this would be it. However, we are now going to use this information and this information to help us solve for C1 and C2. So when we say f of 0 is equal to 4, it means we're going to plug 4 in for f of x, and then x is going to be 0. So if I do that, I get 4 equals 0 to the fourth plus 0 to the third minus 2 times 0 squared plus C1 times 0 plus C2. And this is very convenient because all of these are equal to 0, and we find out right away that C2 must be equal to 4. But the other piece of information was f of 1 is equal to 1. And if I plug that in, I'm going to let f of x be 1 at the same time that I let x be 1. So now I'm just substituting 1. in for everything. Now let's also keep in mind that we do now know that C2 is 4, so I can plug that in here. And now if we just do the math here, we get 1 equals 1 to the 4th is 1, plus 1 to the 3rd is 1, minus 2 times 1 squared is negative 2, plus C1 plus 4. And if we combine like terms here, we get 1 is equal to C1 plus 4. And subtracting 4 from both sides, we end up with C1 must be equal to negative 3. And now I'm just going to take these and plug them in, and we're going to get our specific antiderivative or function f of x. Okay, so we know C1 is negative 3, so when I put negative 3 in here, I get minus 3x. And we know that C2 is positive 4, so we're just going to have a plus 4 on the end. And this is our solution. Next, let's consider a problem involving motion. So here, a particle moves in a straight line and has acceleration given by the function a of t equals 6t plus 4. Its initial velocity, which is called v of 0, is equal to negative 6 centimeters per second, and its initial displacement is s of 0 equals 9 centimeters. Find its position function. So let's remember that when you have a position function, s of t, the derivative of that position is what we call the velocity function, and the second derivative of that position is what we call the acceleration function. So each time we move downward here, we are taking a derivative. If I start with the acceleration function and I want to find the position function, I need to move in this direction. So I need to take antiderivatives to do this. So let's go ahead and perform this now. So if a of t is equal to 6t plus 4, v of t is the antiderivative of this. And that is going to be 6t squared divided by 2 plus 4 times t plus some constant of integration, which I'm going to call C1. So we have v of t is equal to 3t squared plus 4t plus C1. But look what else we know. We know v of 0 is equal to negative 6. So this will allow us to solve for C1. We're going to plug in v equals negative 6 when t is equal to 0. And this gives us C1 is equal to negative 6 because these are equal to 0. And so what this means now is that we know v of t is 3t squared plus 4t, and then C1 is negative 6, so I'm just going to put negative 6 in there. Now, how do we find the position function? Well, to get the position function, we need to take one more antiderivative. So s of t, the position, will be 3t to the third power divided by 3, plus 4t to the second power divided by 2, minus 6 times t, plus a new constant, which we will call C2. Simplifying, we get s of t is equal to t cubed plus 2t squared minus 6t plus C2. And the other piece of information that they gave us was that s of 0 was equal to 9 centimeters. That's right here. And so that allows us to plug in 9 for s of t and 0 for t. And of course, all of these numbers are equal to 0. And so we know that C2 is equal to 9. And then we can plug that in here. And that gives us our completed position function, which we now know is t to the third plus 2t squared minus 6t and then plus 9. In the next example, a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height, and when does it hit the ground? Okay, what's really important here is that we have to start with the acceleration. And the acceleration here is negative 32 feet per second squared. And this is the acceleration due to gravity. So anytime an object is thrown up into the air, its acceleration is negative 32 feet per second squared. So from this, we can get the velocity. So let's just think of this as a of t is equal to negative 32. The velocity function is going to be the antiderivative of this. Well, the antiderivative of a constant is that constant multiplied by the independent variable t in this case, plus our arbitrary constant here. And then they tell you that it is thrown with an upward speed of 48 feet per second. What this means is that the velocity when time equals 0 is 48 feet per second. This is otherwise known as the initial velocity. So we can use that to find out C1. So V is going to be 48, and T is going to be 0, and this allows us to solve for C1, which is going to be 48. So we now know our velocity function is negative 32t plus 48. To get your position function, you need to take the antiderivative of your velocity function. So the antiderivative of negative 32t is going to be negative 32t to the second power divided by 2, plus antiderivative of 48 is 48t, plus another arbitrary constant. But what else we know is that the ball is thrown at the edge of a cliff 432 feet above ground. So the position when time equals 0 is 432 feet. This is the initial position. So this means that we can plug in 432 for s of t, and t will be 0 at the same time. Oh, and let's recognize here that negative 32 divided by 2 is negative 16. So now I'm plugging in t equals 0. And of course, this leads us to get C2 equals 432. And if I plug that back into here, we get our position function is negative 16t squared plus 48 times t plus 432. So now that we have this position function, we can ask the other questions. When does it reach its maximum height? So in this problem here, height and position are the same thing. Let's think about this just for a minute. So the ball is thrown off of the edge of a cliff, like so. It's thrown up into the air. It reaches its maximum height, and then it's going to come down and hit the ground. Okay? So we know that the original height, the initial height, is 432 feet above ground. But from there, it is going to go higher before it starts to come down. So we are looking for the maximum height here. Now, of course, we already know that to find this maximum height, we need to find out when the derivative of this function is equal to 0. Of course, that's the velocity function. And you might remember just from a few moments ago, the velocity function was negative 32t plus 48. Of course, if you don't remember that, all you have to do is take the derivative of this function. And then if I set that equal to 0, this will give us negative 32t equals negative 48. And then dividing both sides by negative 32 gives us t equals 1.5. So what that means is that the ball is going to reach its maximum height after 1.5 seconds. So when does it reach its maximum height? 1.5 seconds later. And that's actually the answer there. They're not asking you to find the height. If they wanted you to find the maximum height, you would plug that in to S, and that would give you the actual height of the ball. So they're just asking, when does that happen? And then the last part is, when does it hit the ground? Well, it hits the ground when the position is equal to 0. So to do that, we have to take S of t and set it equal to 0, which means we need to take negative 16t squared plus 48t plus 432 and set that equal to 0. And from there, it's possible that you might be able to factor this. Let's give it a try. Can I factor out something, maybe a number from all of these? And the answer here is actually yes. You can factor out a negative 16, which will give you t squared minus 3t minus 27 equals 0. And we get really lucky here. This actually factors. Actually, we don't get lucky. I take that back. It does not factor. We have to use the quadratic formula to solve this. So t is going to be negative 3 plus or minus the square root of negative 3 squared minus 4 times 1 times negative 27, all divided by 2 times 1. So what I'm doing here is I'm using the numbers inside the parentheses in the quadratic formula. I can ignore the negative 16 on the outside. This becomes 3 plus or minus the square root of 9 plus 4 times 27 is 108 divided by 2. And this is 3 plus or minus the square root of 117 divided by 2. Now, if you do the subtraction on this, you're going to get a negative value. And that can't be true because we're only looking for a positive value of time. So the answer must be t equals 3 plus the square root of 117 divided by 2. And this is approximately 6.9 seconds. So in our final example here, we will do an example involving trigonometric functions. So here we want to find f, given that the second derivative of f is sine of theta plus cosine of theta. And then we're given two pieces of information over here. So let's start by finding the first derivative by taking the antiderivative of the second derivative. So the antiderivative of sine is negative cosine, plus the antiderivative of cosine is sine, plus our arbitrary constant. Now, if you look over here at the information we've been given, we know that f prime of 0 is equal to 4. So we can replace f prime with 4 and replace theta with 0. And this means that 4 is equal to negative cosine of 0 is 1, sine of 0 is 0, plus C1, and so we get 5 must be equal to C1. So this means that f prime of theta is equal to negative cosine of theta plus sine of theta plus 5. Now to find our function f of theta, we need to take the antiderivative of f prime. So we need to do it one more time. The antiderivative of cosine is sine, so we're going to have negative sine, plus the antiderivative of sine is negative cosine, plus the antiderivative of 5 is 5 times theta, plus another arbitrary constant. And then the second piece of information we know is that f of 0 is equal to 3. We can plug this in here, which means this becomes 3, and theta becomes 0. And we know that 5 times 0 is 0, sine of 0 is 0, and so we get 3 is equal to negative cosine of 0 is 1 plus c2, so c2 must be 4. And so our last thing to do here is plug c2 in there, and that gives us our f of theta, which must be negative sine of theta minus cosine of theta plus 5 theta plus 4. And that concludes this video lesson.